Welcome to Drone Systems and Control, Lecture 13. In this lecture, we talk about transient analysis, transient response of the system. Right? What are the objectives? We'll try to understand what is transient analysis in a control system. We'll also try to explore its importance in drone dynamics, apply transient response matrix to evaluate drone performance, understand the concept of system stability. Here, we are going to give an overview perspective. More detail, one need to look at the control system as a course itself, right? This is more closer to what we use, how we use in terms of flight control design for the multi-rotor system, right? Now let's look at a transient and steady state response. For our, for this particular course, we'll consider only a second order system. Typically, a differential equation of the second order system can be shown in the form of y double dot plus a1 y dot plus a2 y equal to b u of t, right. This could be a homogeneous solution. Then you will have a natural response comes in yh of t is c1 e power minus at plus c2 e power minus beta t, and this is your homogeneous solution. If you look at a particular solution for a forced response for a given input, yp of t will have a structure similar to the input, right. So, we consider the homogeneous solution to get the transient behavior. We try to understand how the transient behavior of this system going to be. That will give us an idea how fast the system going to rise, how close it goes to the final value. This is very important, and how fast it decays to the disturbances, right. The exponentials talks about the time constants alpha and beta, talks about how fast this system response decays. It's all very important if you are looking at designing a controller, right. You will specify the requirement, right. We will say that how fast the drone need to rise, right, how close it has to follow the input. So, the specification need to be translated, and we need to understand whether the existing system satisfies the requirement or not. If not, we need to define a feedback controller. Before even designing a feedback controller, we need to understand how the response of the system is, right. That is why we are just looking at this particular lecture, and we try to see how rapidly the system changes with respect to this. This is also important to just see how quick the system responds to an input, right. So, we need to do. But when time t tends to infinity, these terms vanishes, only the steady state value remains. That is y of t will be tends to a is basically amplitude of the input. For example, if you are taking a step input, a is the amplitude of that, right. So, understand the aspects of it. Homogeneous solution gives me a transient characteristics, how quick it responds, how fast it decays, right. Whereas the particulate solution, the forced response tells me how close the output is output structure similar to the input. So, we can try to understand those. Those are very important to understand the system's behavior, and we can look at the requirement and we can decide whether this is satisfying or not. If not, we need to design a controller to satisfy a specific requirement. Okay. So, now let us look at the transient response itself, right. Transient response is due to the homogeneous solutions, right. It depends on initial condition of the system. It is also affected by the poles, which is basically the characteristic equation. If you look at the roots of the characteristic equation defines the pole location, it also depends on the pole location. Whereas if you look at the steady state value, which is a particular solution which is purely based on the input, right, the structure of the response will be similar to the input. Okay. Now let us take a typical second order system response, right. I am trying to give you an understanding for you, right. I am trying to take a system and I am trying to look at the response over the time and look at the output y of t, right. The blue line talks about how the response goes up, right. Now, what we are interested in, the red one talks about the transient characteristics of the system and its dynamic activity, whereas the green part talks about the long term behavior after the transients has died out, right. So, this is basically our forced or particulate solution. This is our initial conditions, and the poles do affect this response, and we are trying to see how the transient characteristics is, right. Now, shows this particular transient response shows the dynamic behavior. what I meant is how many oscillations are there, how is it rising, how fast it is settling down. These are very important for us to understand, right. In steady state, once it is settles, right, the output behavior, once the transient response dies out, right, it's a long term behavior I am trying to look at, right. Is it matching with respect to my input? Is it satisfying my desired references, right? For example, I can say the speed of the drone need to be increased by 2 meter per second, and I am giving an input accordingly. Is the speed increases by 2 meter per second? After transients died out, settles, I need to look at that also, right. Now let us look at what are the importance of this transient response in control system design, right. So we look at how fast or how accurate the system reacts, right. That is what we are looking at in the transient response, right. We look at overshoot. Suppose I want my speed to go increase from 10 to 12 meter per second. How much it increases beyond 12, right? How long it oscillates? Those are important for us, right? Suppose if you are just looking at a controller you have designed and you want to do obstacle avoidance, right? You wanted to increase your speed, but it overshoots. Instead of 12 it becomes a 14 meter per second and comes back and oscillates, right? Which means the drone come closer to the obstacle and move away. That is not good. So we need to understand the overshoot and oscillations, which could cause an instability behavior, or it could cause a mechanical stress. Think about it, your speed going up and down and it takes time to settle, right, which means your motor will be keep changing the voltage and input, right. That will also cause some vibrations in the whole structure, that will also cause fatigue, right, fatigue cracks and all that, right, or some joints can get loose. So it's very important to understand how much oscillation going to be, how much is the overshoot, right. How fast it settles also is very important. For any given input, the oscillation should die down quickly, right. How fast it settles, that talks about how responsive the system is, right. We need to understand that. We also want to determine how well the system maintains the desired behavior, right. Is there an error? Think about it, you are going in a lift, right, and you want to go to 5th floor, right, and you are pressing the lift to go to 5th floor, and the lift accelerates, right, and goes towards the 5th floor, and instead of stopping exactly on the levels of the floor, but it starts settling lower or higher, is always a problem. There is a likelihood you will tip and fall, right. We want the steady state error to be 0 in certain cases. In some cases we do not mind. For example, I want to go to a particular location, right, and let us say x comma y. I am saying go to 10 meter cross 10 meter. It is very difficult to go exactly to 10 meter cross 10 meter. You can always say there is an epsilon bound. As long as you are in let us say 1 centimeter error is fine for me, or 2 centimeter error or 10 centimeter error. You can define what is your epsilon. As long as you are closer to that, I can say you have reached the goal, right. So this steady state error depends on our requirement, on the case where we are talking about, right. So we need to look at this error to be minimized to satisfy the requirement of the controller, right. Whether you are doing tracking or whether you talk about regulation, you need to understand this and modify the feedback control mechanism such that it satisfies the requirement, right. Balancing between both transient and steady state response is very important, right. So that is where we talk about, once we talk about a controller design, we will go in details about it, right. Now let us look at a typical drone, right. So it could be a quad rotor or it could be a multi rotor system, right. So we talked about different sensors which is already present in the drone. Something is meant for internal, something meant for external, right. You could have a vision camera, or you can have a LiDAR, or you could have a radars, and you could have a stereo camera also. If you look at this vision camera and stereo camera is going to play an important role to get the context in which the drone is going to fly. But if you look at the LiDAR altimeter, it's going to give them very critical information. What is my height at that particular point? And in addition, we talked about internal sensors, which is very important for controller design, right? Inertial measurement unit, global positioning system, right? Inertial measurement unit will have both accelerometer and gyro. Together it will give me the attitude rate and velocity and position information. That's very important for us when we are designing a controller, right? We will be looking at why do we need them. We need to look at fast and accurate control. That's a very important requirement for us, right? It has to reduce the overshoot during a maneuver. If you are trying to go and avoid an obstacle, you just have to follow the trajectory as close as possible. I don't want an overshoot, I don't want an oscillations, because the oscillation can cause me go closer. Suddenly a disturbance comes into picture, I may hit the obstacle, then I have to increase my safety boundary, depends on the oscillation. We will talk about all of this when we go into navigation lecture, right? When we talk about sense and avoid, basically autonomy aspect of it, we will talk about it there. But I am trying to give you a notional understanding. I don't want this overshoot to be present during our maneuvers. I want this whole aircraft to be stable as quick as possible, right? I want that aircraft to track the waypoint as accurately as possible, right? I want to avoid obstacles, right? I wanted to ensure reliable navigation being present, right? Wind is always an uncertainty. The wind gust comes into picture, it affects your thrust significantly, which may lead to change in your position significantly. So I want to have a reliable navigation system so that it can follow. So what we need to do, we need to design a controller, satisfy the requirement, and such that it follows the requirement as close as possible, right? As reliable, as accurate. That's a very important aspect of it. Now in the moment I talk about a system, we talked about mathematical modeling of it in the earlier lecture. We derived that and we show that this, the state of the system, basically the position and velocity, right? Position dot and velocity dot. We derived that, and also attitude and attitude rates, how it changes with respect to input, right? It's non-linear in picture. But if I linearize about a hover condition or about a forward flight condition, I can make it a simple second order or third order or fourth order system. Now various order systems are there, we need to understand their behaviors so that we can quickly interpret if the system boils down to first order, what kind of response we are looking at. Typically if you look at a electronic speed control system which is present in the drone to regulate the speed of the motor, it's a typical first order system. So what do you have? The time constant tau, dou y by dou t, right, plus y of t is equal to k into u of t, right. K is a system gain that you can have, tau is the time constant, the speed response of it, right, y is the output and u is the input. Now if you look at the response, right, for a unit step response, step input, right, I am giving a unit step, I am at certain velocity or RPM, I want to increase, let us say I am at 1000 RPM, I want to increase from 1000 to 1100. How does the system respond, right? So this is how the blue line shows how the system responds, how fast, how much time it takes to go from 1000 to 1100. It takes 4 seconds. Is that acceptable for us, right? That's what we will be analyzing it, and it tells you that it satisfies the requirement or not. If not, we need to design a controller such that this response can be modified. We will talk about controller design in later part of the lecture. And let us say at t equal to tau, right, this is the point, where is it, right, how it is crossing. We can analyze the first order system behavior. It is mostly used in motor speed control, or sometimes we even convert a command which I want to kind of a response for me to track. Having a discrete change is very difficult. Suddenly I can't go from 1000 to 1100, right. Even there we will use a first order system to convert the reference input to a feasible a reference trajectory which can be followed by the drone. Right. If you look at the response of this, if I am trying to solve this solution of this particular equation for a step input, yt will be k 1 minus e power minus t by tau. Now I am trying to analyze this response further. Y of t is k 1 minus e power minus t by tau. I am trying to analyze this further to understand what will happen at t is equal to tau. At t is equal to tau, my y of t will be 63.2% of the final value, right. I can understand that tells me that how fast my system reaches the final value, right. Steady state approaches asymptotically at t tends to infinity. What is going to happen? Look at this particular response. First order system does not have any oscillations or overshoot, right. Where we will use such kind of first order system, I talked about it earlier. We will also use in motor, the electronic speed controller. Sometimes we use this in sensor filtering. If the sensor becomes very noisy, we put a first order filter. We will also use in actuators. We also use in reference trajectory generations, right. So electronic speed controller which is present for motor propeller, which is typically a first order dynamical system, right. But the only thing is tau will be faster, because I do not want the drone to take a 4 seconds to go from 1000 to 1200 RPM, right, but the tau will be much faster. So the response will be very quick, it quickly reaches the steady state value. Okay. Now take a typical second order system, classical second order system. If I talk about it, it is a typical spring mass damper system, right. You have a mass of m, you have a spring constant k, a damper which is a constant b, and you have external force F applied. You can apply the force in towards or away, that is why we put it as a bidirectional. The force can be applied in anywhere, any direction, right. Your displacement happens in, depends on the direction of the force that we are applying, right. Now if I try to write the dynamical equation based on the Newton's law, right, Newton's law, I can write m x double dot, that acceleration m is a mass, plus b into x dot, right, and kx equal to f of t. F of t is the external force, right. And we can apply a Laplace transform. We can assume the initial condition to be 0, right, and the mass is at rest. I can derive the transfer function, and I can write x is my output, displacement is output, f is input, x of s by f of s is the transfer function g of s. It will be like 1 by ms square plus bs plus k, right. Now I can write this in a generic way, g of s, a general second order transfer function. There is a constant k, right, divided by s square plus tau zeta omega n square s and omega n square. I am trying to introduce a new variables here. If you see, I am trying to generalize this equation in a generic form, and I can try to interpret. This omega n is nothing but the natural frequency. It depends on dynamic properties of the system, specifically the stiffness to mass ratio. This more talk about the inertia of the system, right. It talks about how oscillatory, how much oscillation you will have, right. Omega n is for a spring mass damper, it is proportional, is equal to square root of k by m. You have another constant here, zeta, that is a damping ratio. It talks about, it measures how quickly the oscillation decay. It talks about how fast the response die down, right. Zeta equal to b by 2 square root of km, right, at this point of time. So you see, when I try to write the transfer function in a generic form, I can relate the natural frequency and damping towards the physical constants of the system. You can try to understand if the system is oscillatory, what is going to happen. If the system is more have a high overshoot, low overshoot, what is going to happen. You can relate with respect to the physical property present in the system. Okay. So, if you look at omega n, it typically controls the speed, while zeta, it tries to shape or smoothness and overshoot, right. It is more towards the shape of the response, whereas omega n controls the speed of the response, right. Let us try to analyze this little bit more detail. I am trying to represent in a generic form, so that is easy for us to discuss. I am converting our spring mass damper into a general form. Instead of saying x, I am trying to put it y double dot, right, plus 2 zeta omega n y dot plus omega n square y of t and omega n square u of t. Then I can write a transfer function between the output and input y and u. I can get this standard representation of the transfer function, right. What we are looking at, there is a 3 important parameters in the standard second order system: omega n, which is the natural frequency; zeta, which is the damping ratio; k is a DC gain which comes into picture. It talks about how fast the airframe wants to oscillate when it disturbed, how quickly the oscillation dies out, right. What is the command to response scaling, that is a constant k, is all about, right. Now, second order system has poles, right. I can use the characteristic equation. This is a characteristic equation, s square plus 2 zeta omega n s plus omega n square. It is a quadratic equation. We can find the roots of the quadratic equation, that becomes the poles of the system. Here poles are minus zeta omega n plus or minus omega n square root of zeta square minus 1, right. So, we are talking about where the poles are, right. Depends on the location of the poles, we can try to see how the response going to be, right. We can put it in a pole 0 plot, real axis and imaginary axis. I can place the pole. I can talk about if the pole is at a real axis. I can talk about what will happen if the pole is going to be in imaginary axis, right. If you look at the pole in real axis, that is 2 poles, right, in red. If the roots of the systems are real, right, then what will happen? This become an overdamped system, zeta will be very high, right. If pole sits exactly one over other, right, then it's what will happen, right. Or pole in imaginary axis, it becomes an underdamped system, which means it will have overshoot and oscillation. So, I can understand by looking at a pole's location, I can interpret how the response going to be, right. When I say underdamped system, I am talking about the zeta less than 1, zeta is between 0 to 1. Critical damped system, zeta is equal to 1. Overdamped system, zeta is greater than 1. We are talking about if an underdamped, it is going to be oscillatory, there will be a smooth decay. If a critically damped system, it is going to be fast, non-oscillatory. Overdamped system, it is going to be slow, but there is no ringing, right. We will talk about it when we take a typical example and understand better in subsequent slides, okay. Now, let us look at the effect of damping for a typical step input. Usually what we do, right, why I am taking a step as a typical input, right. We want to change the height. Currently at I am 100 meters, I want to go out 150 meters, right. My step is 50 now, right. It is not unit step, here the step is 50 units, I want to go up. I want to understand how the response going to be, right, how the damping ratio affects the response, right. Underdamped system we talked about 0, zeta is between 0 to 1, it will have oscillatory behavior, right. We talk about a behavior in a second order system, it has an oscillatory. Blue line talks about underdamped system, it overshoots and oscillates. For the critically damped system, there is no oscillation, it nicely goes and then settles to the steady state value. Overdamped system, it goes up, it may not reach the steady state when t tends to infinity, right. So, eta equal to 1 is a critically damped system, right. Eta greater than 1, overdamped system, that does not have an oscillation, right. That is a point you need to understand. But other thing is how fast it rises to this steady state. If you look at an underdamped system, right? It rises much faster, right? The rise to the value slows down when the damping start increasing, right? That's another factor we need to remember. Now let's define certain parameters which is very useful when we go beyond this lecture, when we go talk about control system design. See, usually when we talk about a control system design, you need to think one aspect very clearly. The user is going to give the requirement specification. I take a classical example as an elevator, right? You get into an elevator, what is the user requirement? We don't talk about what is the rise time, what is the settling time, what is the peak time, how fast the response should be, how smooth the response should be. No, we just give the requirement in a qualitative sense. I don't want the lift to accelerate much faster. It should be comfortable. You tell me what does that comfortable really translate to acceleration, right? How fast it should rise to the steady state value, right? So that's a bigger problem. So control design, system design, right, requires a capability to translate the user requirement into a specification. The specifications are in twofold, right? How accurately I follow the reference command. When I talk about how accurately follow the reference command, I need to generate a reference command in such a way that it satisfies the requirement, right? How fast the system rises when I give an input to a steady state value. Is there any steady state error? I talked about this. If you want to go to 5th floor, the lift stop at 4.5th floor or like a 0.5 meter error to the level of the floor. You can't go out, or it goes up also is a problem. So you need to know how to translate the user requirement to specification. Then you take a system, model it, look at the responses, analyze the responses, and then understand which response is not satisfying the requirement. And then design a controller in such a way that that has been taken care. Not just only that, rest of the response also should satisfy. So that's what it's all about, right? Now, when I look at a response, I want some qualitative measure to understand. The first one I always talk about is how fast the system responds to the input, right? That's more like rise time, that is TR, what we are talking of, right? TR is like how fast the system respond from 10% of its steady state value to 90% of the steady state value. Sometimes we do it from 0 to 100% also, right? That's the rise time. You see it's marked in green, TR, right? That's what we are interested in. We can, looking at the second order system, we can measure this also. Mathematically we can get a closed form expression. How quick the system initially responds to it. The TR is approximately pi minus cosine inverse of zeta divided by omega n square root of 1 minus zeta square, right? It talks about the rise time. Second important parameter is the maximum or peak overshoot, how much you are overshooting, right? This, or at the time it is overshoot is taking place, is called TP, and how much overshoot is called MP. The steady state value, let's say I want a unit response, but it's just going above this. Let's say it's in this figure, if you see it's somewhere around 1.18, right? So 0.18 is a overshoot. How do we measure this? How much it's overshoots? The maximum overshoot, right? If it's oscillating, subsequently this oscillation will decay, but where is the maximum overshoot take place? I need to figure it out, right? This overshoot indicates the tendency of the system to ring or above the target setting. I want to understand that. I need to calculate that also mathematically. So the MP, right, is e power minus pi zeta divided by 1 minus zeta square. Remember, this is true for underdamped system only, 0 to 1, right? Another important parameter, this is more long term behavior. How quickly the response comes within or closer to the reference value, right? So that's settling time, the time required for system output to remain within specific band. So here you can talk about 2% band, right? or a 5% band. For example, if I talk about 2% band, what I meant, the response should be within, let us say my reference is 1, it should be within 1.02 to 0.98. If I talk about 5%, it is 1.05 to 0.95. How fast it comes and remains within that, that is my settling time. So, I am trying to take that information as a TS. Right? It talks about how fast the oscillation dies out, so that the system reach to the steady state, right. That is also important for us, right. 2% band, if you use TS is 4 zeta omega n, right. Now, the transfer function what we picked up has only poles, there is no 0. But if 0 comes into picture, it also affects the response, right. 0 affects the kind of transient behavior that we could get. So, we try to look at it, if the 0 is real and close to the origin, right. If the 0 is real but between 2 poles, there is a 0 but it is far away from the poles, what will happen, right. So, if it is far away from the poles, right, then what will happen, there will not be any change, there is no effect of that particular 0. But if it is between 2 poles, there will be a change in behavior. But if it is closer to imaginary axis, the response gets affected significantly. So, we need to understand where the 0 is. Okay. Now, we look at the effect of damping ratio in a summary. If you look at what we do under damped system, if it is a complex pair, it rises fast, oscillate and decay. If it is a critical damped system, rises fast but not oscillatory. Over damped system, it becomes sluggish, right. So, if we talk about under damped system, we try to compute what is the time it takes to rise, what is the maximum overshoot that we can get, how much time it takes to die out the oscillation. These are the factors we will be measuring, right. So, rule of thumb is always there, omega n is higher, it is faster. We talked about it. Natural frequency talks about the speed of the response, right. Zeta talks about the smoothness, how fast the oscillation dies out, right. Now, let us consider drone, right. Well, let us consider yaw system, yaw subsystem itself. I am not going to take the complete dynamics of the system for the analysis of the transient purposes, right. I am going to look at the yaw subsystem alone. What I am interested, R dot, right, it is the rate, it is again a nonlinear function, it depends on R, omega d, Vd, theta d, and omega d dot is also a function of this, right. What is yaw rate? I am looking at rate of change of yaw rate, that is a rotational speed around vertical axis. Omega d is a differential rotor speed, the difference in speed between the opposite rotors, right. Vd is more of motor voltage, input voltage, that is control input, right. Theta d, it is a pitch of the blade. See, think about it, in certain multi-rotor you can control the pitch of the blade, right. If you look at a typical helicopter tail rotor, right, I can control the pitch of the blade, right. And also just understand this, R dot depends on Iz, that R dot is tau, omega d and theta d, and dr of R, and omega d will be again a function of it. Zeta is the net torque that could be present. Iz is a Izz is the moment of inertia of the vehicle at the vertical axis, right. So, dr is aerodynamic damping which is present. We talked about all this in the modeling of dynamical system, right, the drone modeling, we talked about all these things, right. Now, what I am going to do is I am going to take a trim of that particular drone which we are operating, right. We are trying to find out steady state, right. I am trying to linearize the model around that and try to get the expression. So, here what I am looking at, I do not want the torque should be present, right. I do not want the aircraft to spin about it, the yaw rate should be 0, I do not want any rotation, I do not want a differential rotor speed, so that I can just level and flying straight. So, if I am trying to trim, right, So I am trying to find out the linearized subsystem. R dot will depends on NRR, N omega omega d and NVVD. Omega d dot will depends on TR, R, T omega omega d, TVVD and T theta theta d. If you want to understand more about how the linearization is done in details, you can refer to Hover Dynamics and Flight Control Systems of UAV Quadcopter. This was published in American Helicopter Society. You can just go through that. But I'm just for our course purpose, we can linearize the system and get it in a linearized form, and we can try to analyze at that particular equilibrium condition. So these are some stability and control derivatives, NR and N omega. They are yaw stability derivatives. NR talks about dou R dot by dou R when R is equal to 0 and omega d is equal to 0. N omega is dou R dot by dou omega d, R equal to 0 and omega d. So we compute these values, right. Similarly, TR, TD, that is rotor's speed stability derivatives, we try to compute them, right. And NV tau V is a control derivatives for a given voltage input. NV is dou R dot by dou Vd, TV is dou omega d dot by dou Vd, right. We try to get this parameters for a given system, right. So we get this information, try to understand what these derivatives are, how it's going to influence. NR is a yaw damping, a stiffness from angular velocity. It tends to oppose the yaw rate, right. It includes aerodynamic drag and gyroscopic damping from the propeller. N omega is a coupling between differential rotor speed and yaw rate. It captures how imbalance in rotor speed influence the yaw torque. NV talks about control effectiveness of differential motor voltage, how effective the change in voltage causes the change in RPM, which results in yaw rate. Tau R, it is the influence of yaw rate on rotor acceleration, right. It has a negligible effect, usually it's small, but one includes this for a gyroscopic coupling. Tau omega, it talks about damping or inertia of the rotor speed response. It exactly captures how your electronic speed control system and rotor inertia affects the change in omega. TV, motor voltage command change to differential rotor speed. It talks strongly tied to electronic speed control, bandwidth and motor response time. At T theta, it's more about pitch change. It's make more sense in variable pitch. Most of the drones multi-rotor system, the pitch is more or less constant, we don't change. It talks about how this change in pitch affects the thrust and moment rapidly, right. So if I set Vd is a differential voltage, that's more important for me to control, and theta d is 0, there is no change in pitch, then I can write the transfer function of yaw dynamics R of S by Vd, right. That is a response output by input, Vd is a input. I get the equation. You see here, this is a second order system, S square minus NR plus T omega whole bracket S, and then you have this omega n square. You can just think about this is 2 zeta omega n and this is omega n square, and then you have a 0 on the top, okay. So I take one particular motor RPM, okay. I am trimming the whole aircraft at a motor RPM of 150, right. For a typical drone, we have to compute these parameters, and we computed these parameters, and this is what it is, right. If you are substituting these parameters, then your transfer function boils down to S square plus 15.55 S plus 0.775. So I get the yaw subsystems transfer function. So now I can analyze how the response of this particular drone is. I can look at the pole 0 plot. What is a pole location and zeros location, right? I have one 0 at 2.74, I have one pole at 15.55, and I have another pole at 0.05. If I try to plot this, right, there is a pole very close to imaginary axis, there is one pole very far away, and there is a 0. But if you look at this 0 is also very far from the pole location. So because you have a pole very far away, even though it is a second order system, it tries to behave like a first order system. Even though there is a 0, but that 0 is far away from the pole, most dominant pole, which is closer to the imaginary axis, right, is far away, the 0 does not play any effect. So even the yaw subsystem, even if it is a second order, the response of the yaw subsystem will look like a typical first order system. Let us look at the response, right. If I try to plot, the omega n comes out to be 0.88 and zeta is very high, 8.84, right, it is a over damped system. If I try to see a response, it just goes like this, right. So I can, looking at the transfer function, I can analyze what is going to happen, what is going to be the damping and what will happen. Think about it, if I am going to, some reasons my eta r is changed, right, I can influence the system, right, if the pole can go closer and closer to the imaginary axis, then which means my yaw dynamics is oscillatory, right. So we can try to understand its effect, what we can do, how we can manage that. If it is an underdamped system, we can just see that it starts shaking because you have oscillation, right. If it is a critically damped system, it rises slow, right. You need to have a trade off between how fast system rises and how aggressive you want. If it is a over damped system, it becomes very sluggish, whatever the input it gives, it is not going to respond. It is more like a bullock cart when you are driving a bullock cart versus bicycle, right, that is very important. When do we use such kind of system? For what purpose we will use? So we have to understand that, right. Now one last topic, I am not going to go into details of stability and all this, I am just going to define stability here, we will look at the details of stability in next lecture. Stability, when I talk about a stable system, think of a ball is perturbed, the ball will start moving up and down and finally sets down at the equilibrium point. No matter how much of the disturbance it gives, it goes back to the particular point, then we can say it is a stable, right. You perturb the ball, it oscillates, but eventually returns to the bottom, right, which typically I can connect this stability to the poles of the system. All poles lies in the left half of the complex plane, that imaginary axis is there in left side of the imaginary axis, then I can say system is stable, right. I look at the step response and how response will decay over a period of time. Now if you look at a ball being kept on top of the cone, the equilibrium point looks stable, but even a small perturbation, what will happen? The ball rolls down and move away, right. A slight disturbance can take the equilibrium point out, the ball rolls away, it is unstable, right. At least one pole lies on the right half of the complex plane. You can have another condition, you can say more than one pole lies on the imaginary axis also will become unstable, right. What happens? The response becomes growing unbounded. So to understand more about stability, analysis of second order system or analysis of linear system, linear time invariant system, you want to understand, maybe a good idea to have a course on control system, because we will focus more towards flight control design, flight controller design, particularly for multi-rotor system. I am just giving you a recap or overview of the stability, how it is and what it really means, right. I am not going into the detailed definition and analysis of that. A critically stable system, you could have a system remains stable under all the condition in the input energy or any initial conditions. It becomes unstable if the gain just goes slightly on that cross over the threshold. So that is a point you need to look at. Marginally stable system, It is disturbance caused motions neither grows or not dies out. It keep oscillation comes into picture if at least one pole lies on the imaginary axis but not repeated. That is what I am trying to say. If only one pole is there, you could have marginally stable system. Now coming back to your subsystem, this is our transfer function, right? We have two poles, one is at 15.55 and another one at 0.05. If I do a pole 0 plot, there are two poles, one is at 15.55 minus 15.55, another one is minus 0.05 and there is a 0 minus 2.74, right. Now the poles lies left of the imaginary axis, so the system is stable. But if you look at it, there is one pole closer to the imaginary axis, right. What will happen if this particular pole, right, if it corresponds to the variable nr, the nr is close to 0, right, the aerodynamic drag, right, the drone starts going to spin about its own axis, making the system become marginally stable, right. The yaw stability is critical here, that is what I am trying to say. Okay. Coming to the end of the lecture, so we talked about transient response, how it is dominated, right, how the poles going to influence, how the initial conditions going to influence, right, and we discussed about underdamped system where damping ratio is between 0 to 1, and we looked at the step response, I look at the oscillation, how much is the overshoot, how fast it settles down. We looked at rise time, overshoot, maximum overshoot and settling time, right. We looked at the critically damped system, we looked at the transient response, we looked at the measures, because these are very important to design how later on if it does not satisfy the requirement, how do we design the controller so that the rise time is improved or overshoot is reduced or settling time is improved. We will discuss all that when we go into flight controller design, right. We also looked at the effect of 0, because you see a transient response. We could have 0 which is unstable 0 and all that. I am not getting into all those details. Those who are interested in and understand the effect of it, they should take a control system course. But looking at our dynamics, I am looking at what is more relevant and then trying to explain those zeros do have effect. We need to understand how it is affecting the transient response, right. And we also looked at the stability definition, and stability mostly we determine on the poles of the system here, right. And that is the end of this lecture. So some reading material I am giving, you can look at Modern Control Engineering, Ugata. It is a good book if you want to understand more about control system, or you can look at the feedback control of dynamical system or control system engineering by Norman Nice. Any of these 4 books will give you a detailed understanding of system responses and stability in detail. Thank you.